Today we have Xiaofeng to talk to us about the QCD critical point and the net proton number fluctuations in the context of star BES2. Xiaofeng, I believe, is familiar to almost everyone here. He did a PhD at USTC and was also partly at LBL during that time. And after that, he did a postdoc at Hosang University of Science and Technology, and was also a visiting professor at University of Tsukuba and also UCLA during that time. Right now, he's a professor at Institute of Particle Physics at CCNU. So yeah, and he has been over the past several years leading the research on the measurement of the net proton number fluctuations and critical point search for the QCD critical point. So with that, I'll let Xiaofeng take over the Zoom room. Xiaofeng, please go ahead.
Yeah, thank you very much, Suraj, for this nice introduction. And actually, yeah, I am very miss Berkeley because I spent almost 3 years there. So I'm familiar with many old friends and places, and yes, and also the beautiful view there. So sometime I think I will go back there and to meet all of you. Okay, today I'd like to discuss about the QCD critical point and net proton fluctuations, which is at the dawn of the RIG beam energy scan 2. And this is a QCD phase diagram. Actually, it basically describes the emergent property of the strong interaction. And the y-axis is temperature, the x-axis is baron chemical potential. At this extreme high temperature, actually, it connects to the early universe evolution, which will have very high temperatures. And at this direction, and with a very high baron density region, will connect to the very dense astral object, for example, the neutron star. So what will happen in between? So that's why we want to study. From lattice QCD, actually, that at the zero baron chemical potential, the transition between hadron gas to quark-gluon plasma has been proved to be smooth crossover. And well, at large mu-b region, it is based on QCD model. Many QCD models suggest that there is of strong first-order phase transition. Then that's in between, there should be a QCD critical point. And then the question is, where is the critical point? And also, the how can we map out the first-order phase boundary experimentally? So I think that's a big question. So from lattice QCD, actually, there are many first principle calculations, and you know that they determine this QCD transition temperature, which is 156 around MeV, that at mu equal to 0, and also they determine the Carroll crossover curvatures, which is very small. The latter, they also calculate the Carroll phase transition temperature and pseudo-critical line with the Carroll phase transition temperature is around 132 MeV. And their calculation, their estimation about the location of the QCD critical point is listed here, that the mu-b of the critical point is larger than 3 Tc. And they estimated that the temperature of the critical point should be lower than the Tc, which is 132 MeV. So that's their estimation. And from the other, actually, for example, the Dyson-Schwinger equation and FRG and the PNGL model, there are also many estimations about the location of the critical point. I just do a compilation here that you can see in the early days from lattice calculation, the mu b of the critic point is quite small, around between 200 and 400 MeV. And also the Dash-Schwenger equation, they have many estimation, and but still a large widespread. But most recently, that the Dash-Schwenger equation has claimed they have very precise determination of the critical point around 617 MeV. So yes, but you can see from different estimation, the uncertainty, the uncertainty could be large still. And from experimental side, also in heavy ion collation experiment, people are trying to pin down the location of the critical point. They have think about from especially from theoretical side, they have developed a set of sensitive observables. Many focus on the fluctuations. They historically there have mean PT fluctuations measurement, particle ratio, and also multiplicity fluctuation from different various experiment, Sirius, Star, NA49, but basically they all see some monotonic energy dependence trend. So that's a kind of frustrated at that time, because many observers show zero signal. Actually, this is in many early days already. And so what then what Rick can do? What about Rick can we discover the QCD critical point at Rick? At that time, actually in the early days, 2006, they hold a reconvening research workshop at Brookhaven, and actually many experts on this field has discussed the possibility of taking the beam energy scan at RIC to search for the possible signal of the QCD critical point. I think many experts from LBR, for example, Nu, Fokker, and Yogen are there. So they actually, and also Hans Gill as one of the organizer. So yeah, they have many discussion to for example, the machine and the sensitive observable. And actually the Rajakov have a hand drawing presentation. It's very nice that he said the title is Can We Discover the QCD critical point at the RIC? And the importance of that is because it's the mapping the phase diagram, finding the landmark that would go in any future book on QCD. Can RIC do this? Yes, if accelerator and detector capability permit measurement of the event-by-event fluctuation of the hadronic observable, and at a sequence of the energy. If nature is kind and puts mu b of the critical point lower than 500 MeV. If yes, the landmark discovered, our map of the QCD phase diagram, then altered by experiment, assuming reasonable progress in lattice QCD quantitative comparison between theory and the experiment for the critical point of the mu b is possible. And in future, fair and can study the first order phase transition. So at that time, actually, people have many view and innovation on this critical point search. And in later, actually in 2008, INT held a workshop, and the organizer Fokker, Ganser, and Misha Stefanov, they have organized this workshop, and many, you see, interesting talks. And actually the actually the race is on between theorists and experimentalists on the search for the critical point. And from experimental side, and Star has proposed the beam and scan program to PAC, but we need a sensitive experimental observable. So people are excited at that time. And the history of the higher order fluctuation observable, actually, it's not jump out suddenly. The observable has gradually developed. And I found the first paper is starting from here. Yoshihata, and here has a collaborator, has discussed the quark number susceptibility near the quick point. And they are discussing the high order fluctuations. Then later, the Hata and the Misha has a collaboration work about the proton number fluctuation. Then the Frijov, Christoph, and their collaborators have the hadronic fluctuations as the Qcd phase transition signal. Then in 2008, actually, after the INT workshop, Misha wrote a paper about the non-Gaussian fluctuation near the Qcd quick point. I think this is first paper described the the higher moments measurement can be done could be done in beam scan as an experimental observable. I mean, it's more like experimental observable now. And then the third moments of the conserved charge, and also the higher moments. That's so after the 2006 workshop at Brookhaven, the BS first proposed, and later the BS campaign formally started in 2010, and the BS2 actually officially requested in 2014 and started 2019. We already know that. The beam scan program at RIC is looking for the turning of the QTB signal, and also mapping out the first order phase boundary, search for the possible Qcd quick point. And our entire beam scan program are very successful, and we have finished 13 energies. Now the last one, the second last one, 7.7 GeV is running. The last one should be 17.3 GeV, which is already accepted for running. And yeah, you are very familiar with the star detectors with large uniform acceptance and the middle rapidity and excellent particle identifications, which is very suitable for the fluctuation and correlation analysis. From 2010 to 2017, STAR has successfully completed the first phase beam under scan, and they have taken 9 energy data points from 2200 GeV down to 7.7 GeV. And the STAR has very uniform acceptance and for different energy and particles. And you can see on the right plot for different energy, at middle rapidity, the acceptance is very similar. And by doing this energy scan, we can access the MUB region spanned into the from 25 to 400 MeV. So we can access the Qcd phase diagram by a large energy range. Since actually second phase of the preliminary scan has been started in 2018, that actually STAR has 3 major upgrades, which is in ITBC and Kaptov and the EPD. These 3 detectors actually can enlarge the rapidity acceptance of STAR, improve the particle identification, and also enhance the centrality and the event plan resolutions. They have been very successful and very important for second phase of the preliminary scan. And also to gain even lower energy below 7.7 GeV, and STAR has running into the run as a fixed target experiment. And this is a data point we have collected And this, the lowest energy is 7G, which can extend the mu-B up to 720 MeV. This is really allowing us to explore high burn density region. I just gave a list of the data taken and will be taken in the future, and you can see that we have STAR has collected amount of good quality data set, span a large mu-B region. So the data is almost ready, and 7.7 GeV is ongoing, is almost completed its goal, and the 17.3 GeV will run in after 7.7 GeV with 250 MeV, 200 million events. So in the following, I will discuss the physics result from the beam scan, and mainly focusing on the high order fluctuations. Before that, I describe you about the some basic measurement. You can see that it's a particle and then particle production and result dynamics. And we have published two spectral papers from beam scan 1. One is the light flavor particle paper and the strange hadron production papers. Based on those particle spectra, we can do some blast wave feed to extract the kinetic result temperature and velocity parameters. You can see the anti-correlation between these two parameters. That means you have a long duration of the expansion, more energy converted into the motion kinetic energies. That's why you have a large beta value here and show anti-correlation. And we can also do thermal feed to the particle yield to obtain the chemical result temperature and the baryon chemical potential. And comparing this data extract from STAR data and also lattice calculation, we can see the mu-B, the chemical result mu-B and the temperature are close to phase boundary below mu-B below 300 MeV. That means we are close to phase boundary, give us possibility to search for the critical point and the phase transition signal. Yeah, so for high order fluctuation of conserved quantities, this is proposed because it can describe the shape of the distribution, especially the tails. And the high order fluctuations are very sensitive to the correlation length of the system. And that's they believe it has high sensitivities. And if we take the cumulative ratios of those volume parameters can be cancelled out, so we can build up the connection between the experimental measurement and the theoretical calculation, for example, fourth order and the third order. From the lattice Qcd calculation, the mu-B equal to 0, when we increase the temperature, you see this fourth order fluctuation show rapid change. That means indeed this fluctuation, baryon number fluctuation are sensitive to the phase transition. There's what would we expect from the theoretical side, the signature of the Qcd critical point when we're passing through the critical region? This actually is a hand drawing from Misha Stefanov, assuming a static and infinite medium. When we're passing through the critical region, the fourth order fluctuation will show up this non-monotonic oscillation behavior. First, enter into the negative contribution region, and then you will see a dip. And when you get closer to critical point, then you will blow up and see a peak at even lower energies. But as actually Ben Mueller have discussed yesterday, many challenge and caveat exist. The high order fluctuation, as it is sensitive to the correlation length, but it's also sensitive to many background that should be taken into account, and how to isolate the signal and the background. So they have discussed many, for example, the non-equilibrium effect and also thermal smearing effect. But this non-monotonic behavior, and especially the peak structure, is what we need to be search for experimentally. This two contribution region, the negative contribution and the positive contribution to the fourth order fluctuation, has calculated and performed a calculation by many groups and many effective models. For example, PQM, 3D Ising mapping to the Qcd phase diagram, FRG, functional renormalization group, NGL model, and even the normal nuclear matter introducing the van der Waals interaction. That means if your system has attractive and repulsive force, they have some competition will result in such behavior. And also PNGL model. So I think this feature is really dominant by symmetry and universality of the system, give you similar feature of these fluctuations. Then STAR actually performed the first amendment and really introduced this theoretical predict observable into experiment, and real merit is starting from 2029 and to 2010. That this actually is part of my PhD thesis research at Air Being Air, which is under supervision of the Hans Gill and Lu. We have done, this is before beam scan starting. At that time, we have a test energy of 19.6 GeV. We have two high energy, 130 and 200 GeV. So basically, this is some facility, some study that this observer can be really measured in STAR and search for critical point. And we, at that time, we have no evidence for existence of the Qcd critical point at mu b is lower than 200 MeV at this region. It's almost flat. Here I show we not only measure net proton but also net charge and net Qiang, and in the beam and scan 1, I just list some details over here. Kinematic cuts, PID, we use both TPC and the time of flight. The centrality definition is very should be very careful because you have to avoid autocorrelation, and also you need to maximize your acceptance to allow more particles entering into your particle definition, centrality definition, to reduce the volume fluctuations. During this analysis developed that we have started to measure the experimental observable more precisely. We need to have carried out some, for example, to it's how to precise measure its estimate the statistic uncertainty, and need to carefully define centrality to avoid autocorrelation, and perform the centrality beam width correction to suppress the volume fluctuation, and do the detector efficiency correction. This is from actually based on many pioneer work from many researchers. For example, Fokker from ABL Fokker has done also a lot of work on this technical part, and also physics discussion about this observable. And so as I discussed with you, that centrality definition for high order fluctuation is especially important, and because it's connected to two background effect. One is so-called autocorrelation, the other is volume fluctuations. The one techniques we are using to suppress the volume fluctuations, which is so-called the centrality beam width correction. If you want to report the result from one wide centrality beam, then you just did not calculate the moment directly from the distribution from that centrality. You just take the net proton distribution for each multiplicity beam. Then you can obtain this cumulant for each multiplicity beam in that centrality. Then you can do the event average to get the averaged cumulants from this large centrality beams. That's what we do, which is so-called centrality beam width correction. It has been approved that actually it can suppress the volume fluctuation effectively. So here I just show you the net proton distribution from 200 GeV down to 7.7 GeV. You can see the mean value are very different. It's due to the interplay between at low energy we have stronger baryon stopping, and high energy we have strong pair production of this proton and antiproton. That's why we see this net proton mean value with strong energy dependence, and also their width. Here I just show you the efficiency of the proton and the antiproton for different energy and the different PT range. We know we need to carry out the efficiency correction. We have to estimate the efficiency value of the proton and antiproton. And basically the efficiency should decrease when you increase the collision centrality due to at central collision you have a larger tracking density, track density, then will lower your tracking reconstruction efficiency. And at higher PT, because you introduce a time flight to identify proton and antiproton, so additional top matching efficiency will be introduced for higher PT proton and antiproton. That's why you get lower efficiency for higher PT than lower PT. The efficiency is important because not only needed for the efficiency correction, but also it's needed for the error estimation, statistical error. You can see how the statistical uncertainty depend on the efficiency number in a simulation. When lower the efficiency, the statistical error will be large, and the high order fluctuation has larger statistical uncertainty compared to low order. The naive expectation is that this kurtosis variance should be proportional, the error should be proportional to the variance of the net proton distribution, but the efficiency are in the denominator. That means you have a wider distribution, you will get a larger error bar, and also lower efficiency, your error statistical uncertainty will be also larger. This has been published in a recent long paper we submit to PRC. This is cumulant C1 to C4 for net proton, and antiproton as a function of the n part. So in general, that since the cumulant are extensive quantity, so they are proportional to the volume of the system. So that's why this is to show some linear dependence. And at low energy, the proton and the net proton result are almost overlap with each other because you have really a small amount of antiproton at low energy. But at high energy, the net proton are small, and the result from proton and antiproton get closer with each other. And so we know that high order fluctuations are more sensitive to the high power of the correlation. And so when system approaching to critical point, we are expecting that there should some anomalous behavior, some sudden change. And for fourth order, for third order, we didn't see sudden change, almost linear. For C4, we did see some anomalous behavior around the 14.5 G and 19.6 GeV in central collisions. But the error bar are also large. So this needs to be confirmed in the BS2 data. But the C4 of the 7.7 GeV, due to its large, we scale 0.5 of this 2 data point. But the error bar of this is also large. We cannot draw a strong conclusion yet. We also take the equivalent ratio for proton, net proton, and antiprotons as a function of the centrality. The C4 over C2 is actually just equal to kurtosis times Lorentz. It's just another expression of kurtosis times Lorentz. This is skewness times sigma over mean. You can see for C2 over C1 and C3 over C2, we see strong energy and centrality dependence of net proton, the red markers here. But for C4, for central correlations, we indeed see some anomalies here from this point to this point. But as I told you, the error bar is still large. This can need to be confirmed with BS2 data. This is energy dependence of skewness times sigma and the kurtosis times Lorentz. This is just equal to C3 over C2, and this equal to C4 over C2. You can see that for C3 over C2, it has strong energy dependence, right? And this is because C3 over C2 is of net proton is connected to the asymmetry of the proton and antiproton production. So at high energy, we have a strong asymmetry between proton and have a small asymmetry between proton and antiproton. That's why you see the value is smaller. And for kurtosis times Lorentz, we see non-monotonic behavior with a 3.1 sigma significance from the statistical analysis. We found that there show up some deep and then a rise for this kurtosis times Lorentz, but at energy below 20 GeV, the uncertainty are still large. And in BS2, we will have 10 to 20 more times statistics that will shrink the uncertainty of this full energy into this green band. Yeah, we see some hint of some hint and interesting behavior, but still we cannot make a strong conclusion of whether we observe a critical signature or not. This slide just show you we compare with our experimental measurement to many model calculation. For example, the URCMD and also hadron Reynolds gas model with canonic ensemble and excluded volume. And those models have no critical point of phase transition. And you see that when we lower the energy, they all show suppression effect. This is mainly due to the conservation of the baryon number. So actually the excluded volume, we know that considering the volume of the particles, this leads to suppression. It's mainly due to the equivalently repulsive force introduced. It will suppress the fluctuation. And at this low energy, it show up the increase may indicate some attractive force enter into this collisions. But we needed to have more precise measurement. By having the comparison to this, we can actually convert the proton and antiproton cumulants into the correlation function. By doing this, we can help understand the different contribution to this cumulant. We know that you see that for a second order cumulant, it shows negative, but it is mainly dominated by the second order, or by the two particle correlation. which is dominated by the baryon number conservation. And also the C3, the third order cumulant. This shows this negative value is actually, you see here, C3 is also connected to have a contribution from two-particle correlation. This large negative two-particle contribution will affect this third order cumulant. But for this three-particle correlation, it is around 0. Within a current uncertainty, there is no strong deviation from 0. That means this large negative value from third order is mainly coming from the two-particle correlation function, which is dominated by baryon number conservation. But for C4, still it has contribution from four-particle correlation, three-particle, and two-particle correlation. If we only if we only look at the four-particle correlation, so it will show some at 19 GeV and 27 GeV, it should below 0. At below 20 GeV, it rises up. But the error bar is still large, you know. So no, it's no significant deviation for this four-particle correlation from 0. If we indeed conclude some structure, we need to have a more precise measurement in BS2. And high order, for the high order fluctuations, and you know that the higher order fluctuations are more sensitive to the Qcd phase transition. The fourth order, sixth order, and eighth order, you see that the comparison from the FRG to the lattice QCD, they are pretty consistent with each other. And we in this computation, they also compute to higher mu-b value. You see, the higher mu-b, you see larger oscillation behavior. That means the at higher mu-b, the fluctuation are larger. And also the high order fluctuation get your stronger signal. And the C6 and the C8 may become negative. You see that when the phase-out temperature are close to this Carroll phase transition temperature, it will become negative. Thus, this negative experimentally we can measure. If we measured, it could serve as experimental evidence of the Carroll crossover. The star in Seport as report, and the fifth order and the sixth order Net-Proton fluctuation from BS1. You can see that the blue point are from 0 to 40 centrality, and this diamond is from 70 to 80 centrality. This is fifth order, this is sixth order. And basically, is that in general, we see the result from 70 to 80% of the peripheral collisions positive value, but mostly for 0 to 40 centrality, the results are negative. Actually, lattice QCD and FRG in this plot calculation has predict a negative value due to the transition between partonic and hadronic phases. However, the statistical uncertainty from experimental measurement are still large. We hopefully in BS2 we can shrink the uncertainty and can have a more strong and a stronger conclusion. We also reported the PP collisions in Seport that we can see. This is C4 over C2, C5 over C1, and the C6 over C2. For PP collisions, this is this multiplicity dependence of the PP collisions result. It follows the trend of the GoGo 200 GeV result. And gradually, when you go from low order to higher order, you can see that the central collision of GoGo collision enter into the negative region, which is the shadowed band. That means indicate indeed that central GoGo collision, there's some interesting may indicate that some interesting happen. And we also compare this result, PP result to PCR calculation. There show some deviation. You see here, not. But for lattice calculation are also shown in this plot. With large error bar, it's consistent with the experimental measurement. In the second phase of the binary scan, we have completed the data taking of 9.6 GB up to 19.6 GB. Now, 7.7 GB is data taking is ongoing. We will achieve the goal around at the beginning of the May, and after that we will take the 17.3 GB, and that is to confirm that we can have the precise measurement below 20 GB to confirm this whether we will see a peak structure or not at low energies. And we have also this fixed target mode energies will fill in this fit into this energy range, and to see whether there is a peak structure or not at this energy range. And why I would like to also discuss with you a little bit about why we take this 17.3 GB, and you can see that the kurtosis times variance of Net-Proton show this non-monotonic behavior, but still, when we plot as a function of the mu b, we see still a large gap between 19.6 GB and 14.5 GB. And so that's why we want to take a thinner scan between these two energy, and you can see this sudden jump. So hopefully we will see some interesting behavior between these two. So that's why this is from two scenarios. Actually, this is my personal dream and hypothesis. If we have scenario 1, the 7.3 GB may just sit smooth in between these two energy. And the scenario 2 that still sit into smooth between these two energy, but the peak structure is here. And for scenario 3, if we are lucky and the nature is scanned, we may see large increase in 7.3 GB due to this narrow critical region. When we just hit the critical region, then they will show large enhancement. So, but yeah, this line is a hand drawing, and these are all hypotheses. So, just not stand for my personal take. Okay, this is my summary. So far, STAR has carried out many interesting measurements from binary scan phase 1 of different experimental observable. From all those observable, actually, we both see the interesting structure, deep, peak, and deep, peak, deep, around the 10 to 30 GeV. So it's difficult to think that all those structure at similar energy range is coming from different physics contribution. So the nature thinking that they come from some common physics, because they are all related to the fireball dynamical evolution, and also the correlation and the fluctuation of the system. So it will be interesting, yeah, if we have a more precise measurement in coming BS2.
Thank you, Xiaofeng. Oh,
okay.
Yes. Oh, sorry. Okay, go ahead.
so this is my last slide. Sorry, and in future we have many facility worldwide built up to explore the phase structure at high burn density. And at low energy, actually, the fixed target experiment is more effectively to search for the to running and gain high luminosity. So yeah, please stay tuned for the exciting physics from the RIC BS2. That's all. Thank you.
Okay, thank you, Xiaofeng, for this nice presentation. Time for questions. So yeah, I see one hand. Please go ahead.
Hey, Xiaofeng, this is Volodya. So thanks for the nice overview. I have a question to the slide with the correlation functions. I think it's slide 30 or something.
Yeah.
Maybe even a couple of slides. So if I look at the antiprotons and two particle correlation, it looks like there is a bump at 14.5 GeV, and it looks to be statistically significant. So maybe you can comment whether there is some understanding of this feature.
Yeah, that's 14.5 GeV. Yeah, you know, it also reflect into this fourth order, right? A proton.
Possibly, but fourth order has this large error bar so far.
Yeah,
but antiprotons looks really small error, so looks really statistically significant, and this kind of looks like a sudden change with collision energy. So it's always interesting if it's something real, this type of sudden changes. So okay, so not really at the moment, not really a comment, I guess, from your side.
Thank you. I think yeah, that's also interesting that sitting at 14.5 GeV. You know that we also see this curtailed time variance. So 14.5 GeV see some interesting behavior, increased behavior, but this need to be confirmed with BS2 data. You know that in BS1 data, 14.5 GeV, we have HFT there that will provide more material. So in BS2, we may indeed confirm this.
But I think also interesting here is that actually the bump it's more like less signal than more signal, because it's closer to zero for antiprotons, right? Like for protons, you're saying there might be a bump in kurtosis, like a signal of something, and here it's like the opposite. At 14.5, antiproton K2 is closer to zero than other energies, so it's sort of the opposite effect from protons, right? So weaker correlations than than at other energies. Okay.
We will investigate more about this. Definitely, it's interesting. Yeah. Thank you for pointing this out.
Thank you.
Thank you. I saw Walker had raised his hand. Walker, did you have a question?
Comment, but after Xiaofeng said that HFT was in there, because I remembered you also showed the centrality dependence for 14.5, which had sort of a little bump in there, right?
Yeah.
And so, but that might be all the HFT. So that could be, I mean, these are different kind of data than the other. So it's better to take them again without the HFT, because that might cause all kind of trouble, right?
Yeah, indeed. Yeah, BS2, we take out the BS2 14.5G, we take out.
Yeah, right. Okay. That I didn't know. That's important information. Thank you.
Yeah. So,
Xiaofeng, there was a question during the presentation on the multiplicity dependence of efficiency in the chat. In the star measurement, do we take care of the multiplicity dependence of the efficiency?
Actually, the efficiency plot I put here is averaged within one centrality. Actually, in real moment calculation, we actually, because we will do centrality beam width correction, actually the efficiency evaluate multiplicity by multiplicity there. Yeah. That's
thanks.
Yeah.
Okay. I don't see other hands. Are there any other comments or questions for Xiaofeng?
Yeah, maybe I can ask another one also related to what
Yes,
I wrote
please.
in the chat. Yeah, thanks. So it's Net-Proton versus Net-Baryon, and it's a general question, but also you had a comparison like this when you showed multiplicity dependence, I think was it in PP or something? When you also compare to lattice data at high multiplicities, right? Yes, and the thing is that well, there is a method, I think you know it, this method from Kitazawa and Asakawa to reconstruct baryons from protons, and essentially this is kind of applying one more efficiency correction, essentially, right? That's how their method works, and I could imagine that if you do this, for example, to correct your proton data, or do this the opposite way and try to correct lattice data for this difference, then this would move these results. Either protons, I think, could go quite a bit down, even to more negative values, or net baryon from lattice would go up to closer to this Scalam limit or something like that. And in order to do this correction, one needs this factorial moments of proton and antiproton distribution. So this is something you have in data, but this has not been done or shown, at least in the paper or in the talk. So my question is whether you plan to do this, or maybe you can just publish this factorial moments and we can do it ourselves and see what's the effect. So can you comment on this maybe? Sure.
Well, yeah. Indeed, within STAR, we have some kind of discussion about whether we need to apply this correction to obtain the net baryon fluctuations. We have some discussion, but not decided yet. Yeah, so we will definitely discuss it again.
Okay.
But in any case, please publish all factorial moments as well. Then you don't have to decide whether you want to do this, or people can make a fool out of themselves.
Yes, yes. Can I make a comment? We tried. We do have preliminary results. So as you mentioned already, this is like efficiency again correction. So by factor of 2. So and effectively the data points, as far as I see, preliminary result for all this energy dependence. Data central point doesn't change much, but the error bar increased dramatically. So it's almost no effect, but the error bar becomes much larger. So to do that correction, I think for BS1, I would say it's out of the question. We cannot really present that, but for BS2, it depends on the statistics. We will see. Yeah. We can do that. This is, I don't not remember. Okay, so that answers Volker and Volodya.
Yeah.
For this plot, someone argued as a series, I don't remember who, if we, let's say, use Net-Proton instead of Net-Baryon from model calculations, that should be more negative. But I don't remember the argument.
To Poisson.
I'm sorry?
The moment you go from baryons to protons, you get closer to Poisson because you fold it with another baryon.
Okay, then it goes more positive. Yeah.
Towards 1.
No, towards 1, yes.
Towards 1, yeah. Towards. So that is the effect we would see. Yeah, what I'm trying to say, there's no intrinsic contradictions from this plot. Yeah, this.
No, but if it goes towards 1 significantly, then there is a contradiction. And yeah, I did the calculation. I think probably you're referring to the results I showed at CPOD or somewhere else. And net baryon is, for example, if I obtained kurtosis of net baryon, say at this effect of global conservation included somewhere at 0.5, net protons would be at 0.8 or 0.7. So they would be halfway closer to Poisson than net baryon. So this is a significant actually effect, at least from the theory side.
But I remember the sign would not change.
Well,
it goes towards 1. So if you're negative and you get enough corrections, you go positive.
For kappa 6, yes, we had negative sign for net baryon and positive sign for net proton. for example.
Okay, can you send me the reference?
Yeah, sure.
Okay. Since we are on this plot, I have a question. So this for the protons, the cumulative ratios are not at 1, right? Is this because of this baryon proton difference, or is it some other correlations? And if it is some other correlation, how does it impact the goal measurements?
Yeah, this deviation from unity, that means there are correlation between proton and antiprotons, and right, some additional correlation dynamics. Otherwise, it should be unity. But what's real physics mechanism behind? You can see that from small multiplicity to higher multiplicity, we are approaching to unity, right? So so as a unity, we see that it's a statistical baseline and a thermal baseline.
Right.
So deviation from unity, that means that may indicate your system we off thermal or have some additional dynamics there. But what's behind that still need to be studied.
Okay. But you mean this would be less in higher multiplicity and central goal?
Yeah, this can provide a baseline for study the central goal.
Okay. So I see Dima has his hand raised. Or Walker, did you have another question or comment?
Yeah, just one. I think what I said was just the opposite, right? And maybe Volodya may correct me. So if you go from baryons to protons, then you do binomial filtering and you go towards 1. But if you go from protons to baryons, so you unfold, so the signal is likely getting stronger, more away from 1. That's my prediction. But Volodya might.
Yeah, that's what I think, and that's what we also have in the model calculation.
So just to clarify this, right? So your points and this may be knowing Nu, he likes big signals. Maybe this is the teaser you need to actually do your job. So you have a big signal. If you do it, it gets even bigger. Maybe that helps to motivate.
No, I'm not unmotivated. It just doesn't help if you have a huge error bar.
No, that I understand.
Right. Yeah, you confuse the people. I mean, it's not,
that I understand.
Yeah, I think still we are looking forward to high statistics data from BS2.
Yeah, indeed. Yeah, indeed. Yeah, but keep in mind that. By doing this correction, the conversion, the error bar should be also amplified.
Yes, that's what Nu says.
Yeah.
I have a simple question. Can I ask?
Siwei, can you hold a minute?
Sure.
So Dima had his hand raised before. Maybe, yeah. Is it a comment related to this? If so, then please go ahead.
Okay, I have a comment more of a more general kind. I think that it is fair to mention that the phase transition we're looking at may be a critical point, may be QCD critical point, but may as well be a nuclear liquid gas critical point. Even though it seems to be so far, but the effects of nuclear liquid gas critical point can stretch for quite a part of phase diagram. And all the effects the star is observing may as well be studying critical point of nuclear liquid gas phase transition.
Do you have predictions? Specific prediction?
Well, I think Volodya at some point had specific predictions.
Yeah, I have. We published a paper with a calculation of net-proton fluctuations in hadron resonance gas model. Yes, with van der Waals interactions. So this is so the behavior of kurtosis at these low temperatures is exactly as Xiaofeng, as on Xiaofeng's slide here. at high temperatures, what we observed, there are quite strong effects of interactions, but above 100 MeV temperature, they are dominated by repulsive part of nucleon interactions, at least in our calculation, which was fitted to nuclear matter. So basically, we see suppression of kurtosis due to repulsion at beam energy scan energies. You could argue that this is connected to liquid gas because liquid gas has effect from repulsion and attraction, and at high temperatures, repulsion survives more than attraction. So there might be a strong effect, but it doesn't look at beam energy scan energies like the critical point signature that, for example, Misha predicted, or what we all discussed. Yeah, that was the conclusion that we got from our calculation, including liquid.
Very large, right?
Yeah, MeV is large, but also temperatures are small here, and maybe at 3 GeV it is more relevant, but at 7.7 or higher, you still see repulsion, but you don't see this structure of critical fluctuations anymore. That was the result.
Well, recently we started to play with a model by Agnieszka where she has two phase transitions, where she has both nuclear liquid gas and QCD phase transition. And we can see that nuclear liquid gas is influencing a lot of things. So, including in the beam energy scan region, like at 7.7.
Yeah, but what do you see net effect? How does it look like? Like it's just repulsion, or there is some non-monotonicity? Do you really see some non-monotonic behavior in beam energy scan region? I think you can see non-monotonic behavior at low energies, but not really at beam energy scan.
To some extent, but then it gets killed by the baryon versus proton. So it's, but to some extent, yes, I think we see. I will have to look at our plot because it's mainly Agnieszka's work, but we see some effect from nuclear liquid gas.
Yeah, please also send us the work that we can look at.
Okay.
Yes.
Thank you.
Okay, thank you. Siwei, you had a question?
Yeah. So it's a simple question. So in your Xiaofeng, in your Net-Proton published data, does it include the protons from lambda hyperon decays?
Yeah. Yes, it has. So all those decay products are included into this Net-Proton analysis. We didn't exclude those.
Okay, and then when you compare to model, does the model do that as well?
Model, this model URCMD, right?
For example.
Model, I remember if I'm remember correctly, we don't have a wake decay in URCMD.
Then
but
for fair comparison, you would do that, right? You would no.
But we have a GEM model paper. We studied specifically of this wake decay effect with and without. Actually, the effects are very similar, almost negligible. Yeah, we published.
Okay, that's good to know.
Yeah.
Yeah, thank you.
GEM model. Yeah.
No, not only GEM model. We have several papers discuss the weak decay for proton.
HRG, yes.
The effect is almost no effect for protons. There are strong effects for kaons and pions, but not for protons.
Yeah.
Okay.
Also, HRG publication studied this.
Yeah, thank you.
Okay. I guess there are no more questions or comments. If so, let me thank Xiaofeng again for this very nice talk and discussions.
Thank you.
Thanks everyone for joining.
Thank you.
Okay, we'll see you next week. Okay, thank you. Bye.